Now let's start our evening session. It's a great pleasure of mine to introduce to you Professor Cyril Closset from the University of Birmingham, who will talk to us about comments on BPS quivers, the view from the U-plane. Please go ahead, Cyril.
Thank you, Rak. Thank you for organizing this meeting. I hope to be able to catch up more of it on YouTube. So yeah, this will be about some work, well, some old and newer work, well, oldish, some work with Michele Del Zotto, and mostly based on this paper with Oriama Goreanu at Oxford from the summer. And since this is a mixed audience, I don't know exactly what is the background of everyone, so I will start very slowly, and then please stop me at any time, and hopefully it's not too boring to anyone. So here is the plan of the talk. I will give some intro about what is this about. So it's about BPS quivers, and I will just review what those are in 4D n = 2 supersymmetric quantum field theories. Then I will focus on 5D theories and their so-called 5D BPS quivers that I will define, and then focus furthermore on some rank 1 theories in 5D and their 4D descendants, and finally discuss what I call this BPS quiver from the U-plane in the talk, in the title of the talk. So let us then consider 4D n = 2 supersymmetric field theory, any such theory. And then we know that there often exist Coulomb vacua, so some particular vacua where the low energy theory is in terms of some photon and their superpartners, m n = 2 vector multiplet. So those theories are IR3. They're just some photons coupled generally to massive matters, and then so you have usual photon interaction, and by supersymmetry also some scalar interaction, and the kind of particles are typically dyons, so they both have magnetic and electric charges. And we often have a continuum of such Coulomb vacua, so that's the Coulomb branch. And by definition, the rank of an n = 2 theory is the dimension, the complex dimension of its Coulomb branch. So at a generic point on the Coulomb branch, then we have a spectrum of massive half BPS particles with the usual BPS relation between the mass and the charges, where the central charge here is this kind of formula, where the charges then gamma are the electric and magnetic charges, which I denote by M for the magnetic and E for electric, and some flavor charges. So all those charges are part of a lattice, which will then always be just 2R plus F dimensional, where then 2R are the electric and magnetic charges, as one for each generator of the rank. So in a gauge theory, for instance, you can think of the Coulomb branch, of course, as breaking the gauge group to its carton, and more abstractly, that's just the rank of the 4D theory. So we would have such, in general, a spectrum of massive particles at a given point on the Coulomb branch. And of course, the very hard problem in general is to compute this spectrum. More precisely, what we call the BPS spectrum typically is not the exact masses, because in principle, once you're given the charges and the so-called periods here, you know the masses. But so what you want to know are what are the charges. So here is, for instance, the case of a pure SU2 gauge theory. Then the lattice is two-dimensional, magnetic and electric charges, and you want to know in this 2D lattice which states are occupied. So in the pure theory at weak coupling, if I zoom in like this, yes, we know that there is a W boson from the X mechanism. There is also a Polyakov monopole, and then we know from various arguments the Witten effect, and going down to at least the Seber-Witten work in '94, that there is a spectrum of simple dyons there. If you go at strong coupling instead, most of those states, the dyons decay, and the only stable states are the monopole and this dyon here. All right, so it just so happens that, so in general, as I say, computing the BPS spectrum is a very hard problem, and I could have spent a whole slide reviewing various methods that exist, but I got lazy. Well, but there is no method that works in every case. So there are a lot of methods designed for some classes of n = 2 theories. So one method that, well, one kind of framework that gives a lot of mileage in computing the BPS spectrum when it's possible are the so-called BPS quivers. So that happens that for some type of theories with some spectrum, you can essentially separate, for instance, in this picture here, you could separate all the states, something like this, all the state that you call particles to the state that you call antiparticles. There is always, for any particle here, there is always its antiparticle by CPT. But so if there is such a separation where I can then pick a basis like this, for instance, where all the states then can be reached by using this basis of charges, and well, there is slightly more precise definition in terms of the central charge here that I will not gonna review, then you have a BPS quiver. So such BPS quiver then means that, so roughly speaking, then you have those basis elements like this one and this one, for instance, or this one and this one, really. Which will be stable Abel multiplets. In fact, those are the simple objects, and those are the nodes in the quiver, like here. And then you compute the arrows between nodes in the quiver by looking at the direct pairing between dions. And then all the stable particles arise as bound states of the simple object, and that this become, in terms of the quiver, a question in representation theory. So to illustrate that, again, for pure SU2, the basis states here are the monopole and the dion -1, 2, the node 1 and 2, and they have electromagnetic Pirag 2, right? It's just the determinant of this, the matrix with 1, 0, -1, 2. So there are two arrows, the so-called Kronecker quivers. And quiver representations then, which are some particular assignment of vector space to nodes of the quiver and some particular linear maps between them, correspond to all the possible BPS states. For instance, the W boson will just be the particular state which has 1, 1 here in terms of the vector space. So that's you have one state of one dion and one and the monopole that gives the W boson. More precisely, what you need to do is look at all the such representation of the quiver. In this example, that will be a pi one, so that's a moduli space of representations, and then you quantize this. And the pi one here, quantization of that will give an =2 vector multiplet, massive vector multiplet. Now, when you have a quiver description, it's really valid in general near some particular locus or point, and then you try to extend it until it's not valid anymore. And when you move on the U-plane, you will change what are called stability condition in general, and in the quiver there's so-called FI terms. So what you think, what you should think about is actually the quiver is some one-dimensional n=4 quantum mechanics. It has FI term associated to each thing. So for instance, if I have the W boson here, it will be 1, 1. There's a U1 gauge theory, U1, okay, and 2 chiral multiplets between the two, bifundamental. And so the FI terms then will determine which vacua of the quantum mechanics exists, depending on the FI term, in this case, positive or negative. And that will be corresponding in this example to strong or weak coupling. Whether or not, for instance, this W boson state exists or not depends on some sort of determined condition in 1D quantum mechanics. Any questions about this? Okay. So let me then change tack a tiny bit here, because today I'm mainly interested in 5D theories. So those are n=1 supersymmetric theories, but that's really the same as 4D n=2 in the sense that it's 8 supercharges. It's an essentially isomorphic supersymmetry algebra, and it gives the 4D n=2 when you reduce on the circle. So in 5D, what we know about QFT in 5D is rather limited in terms of pure QFT language, because we can certainly have free fields in 5D and they are conformal. So here I've been interested in conformal field theories. So free field, of course, have conformal. Gauge fields in 5D are not conformal because, well, you can just write the Yang-Mills term, but the gauge coupling has dimension mass minus inverse of mass dimension. So the gauge coupling, in other words, is technically irrelevant. And in fact, there is no other way to, there is no way to write directly 5D interacting theory, which has a free field limit. Because you can write a gauge theory if you want in 5D, but since the gauge coupling has this dimension, it will be an infrared free theory. The gauge coupling then becomes strong at 3 level and by dimension analysis. And so you have a sort of strong Landau pole kicking in directly at the scale of the gauge coupling, of the inverse gauge coupling. So below the inverse gauge coupling, you have a R-free gauge theory. Above it, you're at strong coupling, you don't know what's going on. And so a non-trivial physical question is whether one can have UV completion of 5D gauge theory. And it's still an open problem if you don't have supersymmetry, although there's been some very interesting recent progress from Cambridge and elsewhere. But we know from the late 90s, from the work of Nati Seiberg in particular, that 5D n equal 1 supersymmetry allows then to have 5D superconformal field theories that UV complete those 5D gauge theories with an equal 1 supersymmetry. Such 5D SCFTs generally have a non-trivial modular space of vacua. They have a Coulomb range in the usual sense. Now we have 5D n equal 1 vector multiplet at low energy on the Coulomb range. This is actually a real cone in 5D. And it has an X branch, which is, as usual, an hypercircular cone. And I will have very little to say about Mr. X today. So we'll focus on Monsieur de Coulomb. And as usual, the rank is a dimension of the X branch. So so as I said that, well, there is argument that dates from Seiberg that we can UV complete 5D gauge theory to SCFTs. Those are very strong arguments, but at the same time, they're not airtight because, well, as usual, RG flows is unidimensional. To try to UV complete something is always ambiguous. But we know they exist by a more direct method, which is string theory. So instead of trying to go from the field theory way, you can just define, if you want, 5D SCFTs as a low energy limit of 10-dimensional or 11-dimensional theory, in this case, M theory. So we put M theory on R5 times canonical singularity, essentially a threefold Calabi-Yau type singularity. And the claim is that at low energy in the transverse space to the singularity, you get a 5D SCFT. The one reason we see that is because we can, well, resolve the singularity to a smooth threefold. Then that will, if it's a smooth threefold and 11D supergravity is valid, then we see that we do have low energy U1 vector multiplet low energy, so we get a Coulomb range. And then you need to argue that when you go back to the singular thing, you would have something interesting happening in a non-trivial fixed point. And conversely, if you deform the X branch, it should correspond to going on to the, sorry, if you deform the singularity instead of resolving it, it would correspond to going on to the X branch, but I won't talk about that today. And so geometrically, the rank of the SCFT is just the number of exceptional divisors. So for each 4 cycle in this resolution, so a divisor, you would get a low energy U1 vector multiplet in 5D. All right. So yeah, so that's what I just said. We just will deform the singularity and we go on the Coulomb branch. That's in M theory. Now, what I want to consider today is not the 5D theory per se, but its compactification on a circle that are called DS1 of a 5D theory. And so that effectively is a 4D n equal 2 theory. It's just that it comes from 5D, so there is still some sort of KK towers everywhere. So that's it. But otherwise, it's still a 4D n equal 2 supersymmetric theory that you should consider. The theories, of course, are not conformal because we have these KK towers essentially. So there is a scale set by 1 over beta, the inverse radius. And the real Coulomb branch in 5D then is complexified and becomes an ordinary kind of complex scalars at low energy A, which is the complexification of the real scalar in 5D plus the holonomy of the 5D gauge field over the circle. Then this 4D n equal 2 theory, this KK theory has a special angular structure like any 4D n equal 2 theory. So that means it has a Seiberg-Witten geometry really. The electromagnetic periods, so the low energy scalar A and its magnetic dual, A dual, are captured geometrically by some period of a so-called Seiberg-Witten differential on an auxiliary geometric object, which in many cases you can take to be a genus G curve, which is fibered over the Coulomb range. And we would like to compute the BB spectrum of such a theory. Note that the charge that is here will still be 2R plus F, but now the number of flavor symmetries is the number of flavor symmetries F in 5D plus 1, where 1 is the KK symmetry. Let's see, because now we reduce on the circle, you get extra momentum on the circle as a 4D symmetry. All right. So then I would like to compute the spectrum, or really what we will do is to argue for how we should have the BPS quivers, and then given the quiver, in principle, you should be able to compute the spectrum. So to compute this BPS quiver and the BPS spectrum, we really have a two-step process, which is a very general thing in string theory and in enumerative geometry. First, we look at a larger set of possible BPS states, which we'll call the BPS category. Those are all the BPS states that could happen essentially anywhere on the parameter space. And then we focus on a particular point on the parameter space, so-called stability condition, so a particular point on the U-plane and also of auxiliary masses and so on. You fix those masses, and we look at this point, what are the stable objects inside the BPS category. So in physics language, that's what we do often when I was discussing D terms earlier in quantum mechanics. So it's an F term, D term. The D term gives some extra condition if you want. So for the theory on a circle here, well, the theory here was defined as M theory on a threefold. But if you compactify on a circle, then you really have type 2A on the same threefold, right? And the BPS states, we know what they are in the type 2A on a threefold. The one of interest here on the Coulomb branch are the various D branes wrapping 2, 0, 2, and 4 cycles. So there are D0, D2, D4 bond states in the resolved threefold. And then the claim, which is not from us, of course, in a sense, it's all the way down to at least the work of Douglas in the early 2000s. The BPS category here is the derived category of coherent sheaves on this resolved threefold. All I'm insisting on in the fact that here, for the kind of Calabi-Yau isolated singularities that we consider and their resolution, this whole B-brane category or derived category is really a BPS category of 5D SCFT. So it's a subsector of string theory, but it's also directly a QFT interpretation. So those BPS states are essentially DT invariant in mathematics, although there's been some interesting work by the group here at KIAS over there that insisted on the fact that we should really consider 5D BPS states. So that's important. It's a question of normalization. When you count DT invariant, in general, there will be states that are well, you would count in DT theory, but are not really normalizable in the 5D sense, and so should not be counted as 5D BPS states. Otherwise, you get some kind of state that are not, like, as you've seen in some other talks, in DT type theory, even C3, the trivial singularity would have associated BPS states if you want. But this theory is in 5D SCFT language should be the empty theory, so we better not count that. All right. So if you have then this notion of BPS category as a B-brane category, the BPS quiver will be any quiver with superpotential, such that is a derived category of representations or a derived category of modules of this sparse algebra is this B-brane category. And this is, of course, a long story. I could have cited many people in mathematics and physics to relate precisely B-branes to quiver representations. So for the kind of canonical singularities that we will consider today, which are fully resolvable, or in particular if they are toric, for instance, then we know how to do that. That's the usual fractional brane quivers that many of you are familiar with. So for instance, this is the C3 mod Z3 singularity in the toric language, and the quiver has 3 nodes. This corresponds in this case to a 5D BPS quiver for the rank 1 E0 theory. This is a theory which has no 5D gate shear interpretation. It has just it's just an abstract 5D SCFT. It has 3 nodes, electric magnetic charge if you want, and a third one which will be the KK charge. And then of course, for toric case, we know how to derive them from a famous construction that between that relates that given a toric diagram, let's say you can build the so-called brane tiling periodic quivers. The number of quiver nodes then is always 2R plus F plus 1 in 5D language. It's also the area of the toric diagram, the simplicial area. Now, for non-toric geometry, finding quiver is more of an art, and that's maybe one motivation for what I want to say later. Some powerful method exists in some cases using B-branes, but it's fair to say that for generic singularities, in particular generic canonical singularity, which are not completely understood even in 5D language, to find the BPS quiver, the 5D BPS quiver is still not known in general. There are many cases which are known, but we don't have a completely systematic method. All right. So let me then focus on one simple class of theory where I think we know everything by now. Those are the so-called EN theory. Those are rank 1 5D theory with the EN flavor symmetry. They were discovered by Seiberg and Morrison and Seiberg in '96. They are the UV completion of n equal 1, 5D n equal 1 SU2 gauge theory with n-1 fundamental hypermultiplets. And you can think of this SU2 gauge phase as a mass deformation of the 5D fixed point. So the 5D fixed point has a full EN symmetry, and you break it to SO2n-2 times U1 by just removing this node, so to speak, here in the Deakin diagram. So SO2n-2, of course, is the flavor symmetry when you have n-1 fundamental of an SU2 gauge group or a symplectic group. So, and there is a whole family, 10 of them. You just start from the E8 symmetry, and you can break by various mass deformation all the way to E7, E6, E5 is SO10, E4 is SU5, all the way to E0 here that we mentioned before, which is the trivial theory. At rank 1, then, the electromagnetic periods, A, dual, and A, are related to the period of the family of elliptic curve, right? Those are tori with their complex structure. And the complex structure of the elliptic curve is then, by the famous Seiberg-Witten insight, is precisely the electromagnetic coupling, the effective gauge coupling at low energy. So we then consider the family of elliptic curve on the one-dimensional Coulomb range that gives a two-dimensional complex manifold or complex surface, which is a rational elliptic surface with a section. More precisely, to have a compact rational elliptic surface, we will just compactify the Coulomb range. So this is a U-plane, and we just add the point at infinity so that it's a pi1. The cool thing is that rational elliptic surfaces are fully classified by a person in 1990. So, well, you can look at their list and understand what is the physics interpretation of all of that, and that's part of what we did in gory detail in that paper with Aurea Magoreanu last summer. Here, suffice to say that rational elliptic surfaces are fully classified and characterized, in fact, by two things. One, their set of allowed fibers. So that's where when you have elliptic fibration, right, you have, then it might happen that the torus, the fiber, the elliptic fiber pinches in some way, and how it can pinch is classified by Kodaira long ago. And so we have a set of allowed singular fibers on the U-plane. And to fully determine the rational elliptic surfaces, you also need to consider its group of section, its so-called Mordell-Weil group. We discussed the physics of that in terms of flavor symmetry in the paper, but I will not discuss that today. So when you have singular fibers, then in terms of the full rational elliptic surface S, you would have essentially, well, you would have exactly an AD singularity to which you can associate the flavor symmetry in the usual way, like we do in F-theory. Such AD singularity admits a standard resolution where you have essentially a nodal curve from the pinch, various top of singular curves pi1s when you pinch a torus, and then you will resolve that in a given way, for instance, like this, that will give, for instance, the I5 Deakin diagram. Here it's a resolved pi1 in the elliptic fibration, in the fiber of elliptic fibration. So you would resolve that, that will be the usual Kodaira model of the rational elliptic surface. So the nice thing about this perspective is that it gives us a bird's-eye view of many things we know about rank 1 for the inequality theory. And the basic idea is that, all we did here is to compactify, to add the point at infinity so that we have a nice mathematical problem, but we still need to keep track of this point at infinity. So it's a we just fix the north pole, say, of my base, of my U-plane. And we then fix what is what kind of singular fibers I have at infinity, and up to essentially fixing the fiber at infinity determines which type of theory we're talking about. And in particular, we can show that for the 5D EN theory on a circle, what you will have is a fiber at infinity which is of type I9-n, just like the simplest type of quadrat fiber with a resolution which is the affine 9-n diagram. I should note that you could also have the I0, which is the trivial fiber, a smooth elliptic curve at infinity. In that case, naively extending here, it will be a so-called E9 symmetry, but what you really have, so the affine E8, but what you really have is that the 5D theory in that case is really 6-dimensional, and you get a 6D string theory on a torus. And all the other possibilities for the fibers here at infinity, which are classified by Kodara long ago, are given in this table. And so here is the 5D theories, but all the other possibilities, the so-called type 2, 3, 4, and so on singularities, they all have a 4D interpretation instead, and they can be obtained by Algae Flow from the top. So in particular, in red here, you have the SQCD, so that this is pure SU2. This is pure SU2 theory with 1 flavor, 2 flavor, 3 flavor, or 4 flavors. This is conformal. Those are all SCFTs, the so-called Minan-Minshensky theories, and those are the Arger's last theories of rank 1. This gives the complete list of n=1 SQFTs with trivial Coulomb range. Trivial Coulomb range means that at low energy, I have just a U1 vector multiplet, nothing else. There are also other SCFTs classified by Argyres, Lolito, Liu, and Martone 7 years ago. Those theories are characterized by what they call an enhanced Coulomb range, which means that there are at generic point of the Coulomb range, there are also a bunch of hypermultiplets. And to discuss that, it's been discussed in this paper in particular, but to discuss that in this language, you need a bit more data. So this rational elliptic surface, you can embed it in string theory more naturally by looking at the local mirror symmetry. So our 4D theory was really type 2A on this resolved singularity, or the singularity itself. And then the resolved singularity is any going onto the Coulomb range and massive forming. So as usual, type 2A on a theory with 2 cycles would have worksheet instantons because of the worksheet wrapping 2 cycles. You can do a mirror symmetry where you have a threefold with only 3 cycles, if you're lucky. And this, sorry, this should be B, not A. So that's type 2B on the local mirror will encode all the Seber-Witten geometry, all the Risson instantons for us. And well, you can write it in various ways. This mirror, in particular, you can write it as a double fibration here, like in Orivafa on a so-called W plane. You would have a W plane, there is an elliptic curve on top of it, and another C star fiber. And then in this setup, if you look at the vibration of just the elliptic curve over the W plane, it's isomorphic to this rational elliptic surface I was talking about. So this is literally the Seber-Witten geometry embedded inside the local mirror. And in particular, the electromagnetic period, the electric period, of course, there is a period that depends on where you are on the U plane, A of U. That's a particular function like this, or asymptotically at large U, there will be an expression like this with some sort of incident corrections. And this is what is called the mirror map in the geometric context. So those curves were derived in full detail by Eguchi and Sakai with all the mass deformation in 2002. And the various, in the massless case, you have various singularities that reproduce, in particular, the 5D X branches and their flavor symmetries, which are EN. If you have generic mass deformation, you just have a bunch of I1 singularities, a simple type of non-trivial singularity. You will have NF plus 4 of them for my EN theory, where N is NF plus 1. And similarly, that would be the SQCD in 4D. You can do various zooming in and out in this story, meaning you can do Algae Flow. So there is some interesting algae flow you can do from 5D to 4D, going in this language from here to there, for instance, right? It's very simple to see what's going on in terms of the, well, you can do it at the level of the curve, right? I didn't write any equation in this talk, but here those are complicated rationalities, one parameter family of curves that you can play with. Well, it has one parameter u and then all the mass parameters. So if you tune the mass parameters, in particular, you could go from the 5D EA theory to the 4D EA theory. That just there is I1 singularity essentially that you can send to infinity. Then you change the type of singularity at infinity. You still have a type 2 star singularity in the bulk, which is carries the E8 symmetry and from which emanates X branch, which will be the modular space of E8 instantons. Another type of algae flow you can do is a so-called geometric engineering limit, when you need to first, well, you need to, here in this case, in this example, you would split one of the singularity here further to a smaller singularity times an I1, and then sends two different I1 to infinity at the same time. And in that case, you can go for instance, in this case, what is it? It is 4D SU2. It is 5D SU2 with 4 flavors to 4D SU2 with 4 flavors, for instance. So in many, so those are the Seong curve, that were known for a while, and we can play with it. Now, a very interesting thing that happens is that in many cases, this Coulomb branch or this U-plane is a modular curve. That means that it's isomorphic to a quotient of the upper half plane, which is the electromagnetic coupling tau, by some gamma, which is some subgroup of SL2Z. And in that case, then the mirror map A of U, you can write it as really a relation between U and tau. So in that case, the map between U and the electromagnetic coupling tau would be 1-to-1. And then you can write the Coulomb branch as a fundamental domain on the upper half plane for gamma. So those are examples of for the massless curve in 5D. And they're all modular curve for this particular group. Like for instance, the E7 theory is gamma 0,2. I give an example here. So for instance, the so-called E1 theory, so which is the completion of in 5D of pure SU2 with 0 theta angle. It's a modular curve for gamma 0,8. The fundamental domain for it is written here. It's gamma 0,8 in particular, it index 12 in SL2Z, so you see that there are 12 fundamental domain. I mean 12 wedges of SL2Z glued together. The nice thing about this picture is that you can see very clearly what kind of BPS particle become massless where on the Coulomb branch. So here we know we have singularities when there will be two type of dions that become massless there, and there. But here you can really identify what they are. Essentially, the I1 singularity here will be the point here on the real line. But this is the S dual of the thing at infinity. At infinity, the cusp at infinity would be like an electron, and so the S dual is a monopole. So here we have at U equal -2 here, a monopole. Similarly here, we need to do T2 and then S. So what you will get is a dion of type -1, 2. And similarly, you need to do T4 and then S, you will get the 1, 4 type dion. Then that brings me to the BPS quiver ID. The basic idea here to at this level, let's say, guess what is the BPS quiver description in this kind of theory when you have a modular description is just to consider Coulomb branch configuration which have only IK singularities. IK singularities will always be in this. Well, we can pick a fundamental domain where the singularities are cusp of the modular group on the real axis, and then you will identify which kind of BPS particle you have there. There could be another type of singularities, by the way, in general modular group, which are so-called elliptic points, but those would be like Argyros point in 4D. Well, the low energy description is an Argyros point. So we then conjecture, if you have such a configuration with only IK singularities, that the BPS spectrum consists of dions of charge MQ, which are which are which become massless, which are the dione. What I mean is that each point here, those are different points on the U-plane at which a dione become massless. But we place ourselves, let's say here, for instance, and we assume that we are close enough so that all the dienes from there, and there, they're all massive but stable at this point. That would be a kind of quiver point. That's a conjecture. And so we can pick those states that become massless here as a basis of my BBS quiver, as the simple objective my BBS quiver. And then if that's the case, then we can just compute the quiver by just looking at the arrows, which are again the direct pairing between electromagnetic charges. So this is the pedestrian way of getting the quiver, but not the superpotential. And sadly, I don't know how to compute the superpotential in this way. I mean, there are complicated methods in some cases, like class S and so on, but not in the general case, or not simple enough for me at least. And I should note that this is a conjecture, but in many cases we can prove that this quiver description does exist by computing the central charges exactly of those particles and see what they are at strong coupling. So in my E1 example, I'm running out of time, so let me be right on time. In this E1 example, we just say that there were 3 types of dienes that become massless: 1, 0, -1, 2, and 1, -4. There are 2 -1, 2 dienes. So I'm just writing 4 nodes of the quiver then: 1, 0, 1, -4, and my 2 dienes here, -1, 2, and compute the direct pairing. 2 between this and this. There are 4 in this direction. So that's this quiver. Right. So this quiver is the well-known BBS quiver in this case, for the well-known fractional brane quiver, if you want, for the F0 geometry. And in this case, we can show explicitly that it's valid at the origin of the U-plane. So it's a valid description, valid BBS quiver. So there is a proof that this BBS quiver exists, this BBS point exists. You can do a similar game by just looking at all possible Coulomb branch configuration of all the 5D theories and their descendants, and look at what are the possible modular singular description and so on. Let's just conclude with one example, which is non-toric. So if you look at the Etheory, there is a modular configuration which is like this. There's some I1, I6, I3, I2. I1 is at infinity, but there is I6, I3, I2. That means there is 6 particles of a given type, which turn out to be 1, 0. There is 3 particles of a given type, which is 2, -1, and 2 particles of a given type, which is 3, -1. And then you look at the direct pairing, which is 1, 1, 1 in this case. So in that case, you get 11 node quiver, which is a 3-block structure. So the block means that when I have a block here, all the arrows go like this. So all the possible arrows that I can draw between each blocks, and no arrows within a given block. So this is actually a known quiver, goes all the way to work by mathematician Karpos and Noggin, 94, a known quiver for local DP8. And by the way, if you remove one node here, which is one of the Algae Flow we did before, you can get also a BPS quiver for the 4D E8 Mina-Nemeshansky theory. So that brings me to my conclusion. In this short talk, I revisited a bit the general approach to rank 1 and equal 2 theories in terms of rational elliptic surfaces, and discussed the Coulomb branch physics of the 5D theories, the 5D SCFTs of rank 1 on the circle, and then studied the global properties of that Coulomb branch, that U-plane, especially their modularity, from which we could study the quiver points more in detail. So a more systematic analysis is needed. I should mention that Oria Magorianu will have a follow-up paper appearing on that, where he classify all the possible modular groups that can happen on the U-plane. And here an outstanding question is that we should really compute the superpotential in general in this method. There should be a simpler way to see the superpotential. In terms of the mirror symmetry, superpotential is always some sort of disk amplitude for the topological string for the B model. So for the A model, sorry. So yeah, and then finally, of course, I haven't discussed much, but there should be ways in some cases to relate to and maybe generalize some other approach, like spectral networks for class S or string lattices in the F-theory approach to these theories. Thank you.
Thank you very much for the very nice talk, Cyril. Are there any questions in the audience?